All right, picture this. You've got a massive 30-ton piece of heavy machinery, the absolute lifeblood of a job site, and suddenly, it just turns into a giant, incredibly expensive paperweight. Welcome to this explainer, where we're going to dive deep into a real diagnostic mystery. We're looking at a CAT 320D excavator that just completely died in the workshop. This case study is fascinating. It literally pits digital diagnostics against mechanical reality. And as you'll see, it's a story packed with twists, a few frustrating red herrings, and a massive lesson in troubleshooting that honestly applies way beyond just heavy equipment. So how did this all kick off? Well, the operator reported a critical electronic malfunction right before a complete, total no-start condition. The machine just flat out refused to fire up. And that set the stage for what quickly spiraled into a total troubleshooting nightmare for the workshop. Now, you know how it is. When a machine this complex throws an electronic error code, your immediate instinct is, hey, trust the computer, right? But here's the catch. Trusting the very first thing the computer tells you can cost a workshop a ridiculous amount of time, money, and sanity. Now, before we get too deep into the weeds of this mystery, we really need to understand one crucial piece of the puzzle. This machine uses a HEUI fuel system. That stands for Hydraulic Electronic Unit Injection. This is absolutely critical because it fundamentally drives how the fuel is pressurized and injected into the engine. Instead of relying purely on a traditional mechanical pump to push that fuel into the cylinders, a HEUI system uses highly pressurized hydraulic engine oil to actuate the fuel injectors. So do me a favor, keep this hydraulic-electronic relationship in the back of your mind. It's the absolute key to understanding why these mechanics were so easily tricked a bit later on. Okay, so here's our roadmap. We're going to walk through 4 main diagnostic phases: ECM verification, Jaltest data analysis, a managerial pivot, and finally a mechanical teardown. Our golden rule for all of this: continuous moving. In complex troubleshooting, you can never ever stop at the first solved symptom, because as we'll see in modern engineering, one failure is often just acting as a mask for another. All right, diving into phase 1. Right out of the gate, the team actually did a great job isolating a genuine digital fault. They hooked up their diagnostic tools and found a massive malfunction in the ECM, which is basically the brain of the excavator. And by cleverly removing the wiring harness tip for some isolation testing, they confirmed a critical CAN bus error that traced directly to an internal failure right inside the ECM itself. So, what did they do? Exactly what you'd expect. They went ahead and replaced that faulty ECM with a brand new, fully programmed unit. Bam! Case closed, right? Well, actually, wrong. After successfully programming and installing this brand new, super expensive digital brain, the techs turned the key, fully expecting this beast to roar back to life, but it just cranked. It mimicked the exact same no-start symptoms it had before the new ECM was installed. Now, the ECM failure, that was a genuine fault for sure, but it clearly wasn't the only fault. And this, right here, is the exact moment where that continuous moving process gets put to the test. They couldn't just throw their hands up and give up. They had to force the process forward into phase 2. So moving into the live data using their Jaltest diagnostic tool, things start getting really interesting. This data illustrates a massive, glaring gap between what the computer wanted and what the machine was actually doing. The commanded fuel pressure, basically what the ECM is aggressively requesting just to get the engine started, was incredibly high. But the actual fuel pressure, the reality of what was happening inside the system, it was completely anemic. It was struggling to even climb past 200 bar during cranking. Basically, the engine was totally starving. And that brings us directly to a brilliant, but honestly super dangerous illusion. The mechanics on the floor discovered a pretty fascinating workaround. They noticed that if they physically reached in and just unplugged the common rail pressure sensor, boom, the engine would suddenly start up. By unplugging it, they essentially blinded the computer. This forced the ECM into a default limp strategy map that totally bypassed the need for accurate pressure readings. Now, because the engine fired up with the sensor unplugged, and because the live pressure readings had been so erratic, the floor techs came to a very logical but entirely wrong conclusion. They decided, hey, this sensor's defective, and urgently requested a purchase order to replace it. But right before a new sensor could be ordered, a managerial intervention stepped in and stopped that purchase order dead in its tracks. Instead of just blindly part swapping and throwing more money at the machine, the manager paused and asked a really profound question. Is the actual pressure failing to match the commanded pressure because the sensor is lying to us? Or is it because the physical fuel systems simply lacks the mechanical ability to build that pressure in the first place? I absolutely love this analogy. Think about it. Replacing a sensor just because it reports bad data, is exactly like breaking a thermometer because you don't like the cold weather outside. It's completely missing the point. It doesn't change the actual temperature, and it definitely doesn't fix the engine. You have to look past those digital illusions and really question the physical, mechanical reality of the massive, heavy machinery sitting right in front of you. So, following the manager's directive, the team came up with a new hypothesis. What if the pump timing is off? Now, the techs were highly skeptical about this. Why? Because standard HEUI systems rely primarily on hydraulic oil pressure to actuate the injectors. They lack those strict, rigid mechanical injection timing lines you'd find on older inline pumps. Because of that design, timing is almost never the first suspect for a low-pressure, no-start condition. Honestly, a lot of experienced mechanics aren't even aware of how just a slight timing mismatch can completely disrupt internal pressure generation on these specific C6.4 ACERT engine configurations. But you guessed it, by embracing that continuous moving mindset and refusing to just settle for the easy answer of a broken sensor, they proceeded with a heavy physical teardown. They got their hands dirty. First, they physically removed the high-pressure fuel pump from the excavator. Next, they meticulously inspected the timing gears and alignment marks. And then, the jaw-dropping reveal. They discovered the true, totally unsuspected culprit. The internal pump timing was completely 100% mismatched. Which brings us to this really beautiful realization about digital data versus mechanical reality. The sensor? It wasn't broken at all. It wasn't sending false data. It wasn't glitching out. The sensor was actually the hero of this story. It was accurately and faithfully reporting the exact mechanical nightmare happening inside the engine. It was screaming at the computer that the pump couldn't build pressure because the pump's internal timing was totally throwing off its stroke cycles. The digital tool was right all along, but the humans interpreting it? We had almost totally fallen for the illusion. And the resolution here was immensely satisfying. The techs meticulously realigned those mechanical timing gears right back to the exact factory specifications. They reinstalled the pump, securely plugged that original, perfectly healthy common rail pressure sensor back in, and turned the key. And the result? The engine built instant pressure. The actual pressure matched the ECM's commanded pressure perfectly, and that massive 30-ton excavator fired right up immediately. The mystery was officially solved. So as we start wrapping this explainer up, we really have to look at the true cost of just treating symptoms. Now, to be fair, the CAN bus error in the ECM and the low pressure readings from the sensor, those were 100% real symptoms. But if you stop there, you end up wasting days of labor and just burning through cash. To find the true mechanical root cause, like those mismatched gears hidden way deep inside a pump, you absolutely must enforce a disciplined strategy of continuous moving. You solve one layer, and you immediately ask yourself, okay, what's next? I want to leave you with this incredible quote from strategist Robert Greene in his writings on mastery. He perfectly captures this whole scenario. See things as they are, not as your assumptions color them. In engineering, in business, and honestly in life, analytical skepticism is a massive financial and operational asset. This workshop almost assumed they had a bad sensor just because it was the easy answer. But true mastery requires looking past our digital assumptions to find the grounded, mechanical truth. So as you tackle your own complex projects today, I'll leave you with this question. What realities are you ignoring just because you've assumed the first easy answer is the right one?